So welcome to part 2 of our video on solubility product. So we ended by looking at how you can predict whether a precipitate is going to form or not. So here we have a question. Predict whether a precipitate will form when each of the following is added to 650 mils of a 0.080 molar potassium sulfate solution. Okay, so we have A. If we add 250 mils of a 0.040 molar barium chloride. So I'll attempt to show you how to go about this question with part A, and then you can try out part B and C on your own. One of the key things to understand here is that here what we want to form, if we were to put barium chloride in potassium sulfate, is to form barium sulfate. So we need to be able to find out which two ions are we interested in. So we are interested in the sulfate and we're interested in the barium. So when they form the compound barium sulfate, we are going to have sulfate ions that had this concentration with this volume being added to 250 mils. So the final volume for where the barium sulfate is going to be will be 250 mils and 650 mils. Okay, so let's look at how you can solve that. So the solution is, I can just put it in red. So first of all is to understand that the constituents of barium sulfate are sulfate and barium, and we are getting the sulfate from the dissociation of potassium sulfate. So we have 2K plus the sulfate radical. Now this sulfate radical has a volume that is given here of 650 and a concentration of 0.080. Then the barium, we are getting it from barium chloride, and it will also dissociate as barium, so that is aqueous. It is aqueous 2 plus, aqueous plus 2 chloride ions and aqueous. Also, if you check, you see that here the barium was obtained from a volume of 250 mils and a concentration of 0.040 mol. So the first thing that we have to do is to calculate the concentrations of the two constituents. So the concentration of barium is going to be the number of moles of barium in barium chloride, which will be 250 mils times 0.004 molar divided by our total concentration is going to be the concentration, the total volume is equal to the volume where the barium chloride is, or where the barium is in barium chloride, plus the volume of potassium sulfate, so which is 650 mils. I'm using mils and mils because the mu on top and the mu down cancel out. But if you like, you can actually convert the mils into liters. So we get now 0.00 and 11 molar as the concentration for barium. Then also the concentration for the sulfate will be equal to the number of moles, which we can get 650 mils, times the concentration 0.080, and that is molar, divided by the total volume, which is 650 mils, plus, not times, this is plus 250 mils. Okay, so our concentration becomes 0.0058 molar. Okay, so once we get this, we go ahead and calculate the Q value. So our Q value will be equal to the concentration of barium ions, 2 plus, times the concentration of the sulfate radical, 2 minus. So that will be equal to 0.0011 multiplied by 0.0058, and our Q value is 6.4 times 10 to the minus 6. Now you note here that our Q value, if I can write it back here, so our Q is 6.4 times 10 to the minus 6 compared to our KSP value. So this is greater than our KSP value, which is 1.1 times 10 to the minus 10. Okay, so the KSP value I had given them here, in case you missed it. Okay, it is here for barium sulfate. So we are saying that since our KSP value is greater than the, since our Q value, is greater than our KSP value, it means that barium sulfate, which is going to be produced, will actually precipitate, so it will form a solid. Okay, so you can do the same for the other two questions. Let's go ahead and look at an interesting aspect of the solubility product, or rather solubility, which is the common ion effect. That is common ion effect. So the common ion effect is actually considered to be a special case of Lee-Chatterier's principle. So the common ion effect is where actually you have the addition of a common ion. Now, a common ion is an ion which is already present. So it is already present in the solution and results in the precipitate. Or precipitation of a sparingly soluble ionic compound. So the addition of a common ion, is actually equivalent to adding stress to a system. And that is why we are seeing that the common ion effect is a special case of Le Chatelier's principle. So therefore, the system responds to the stress by reducing the solubility of one of the common ions. And because of this, keeping the Ksp constant. So the idea is to maintain the Ksp constant. Let's look at a problem to try and make this concept make sense. So the Ksp for lead to fluoride is experimentally determined to be 4.0 times 10 to the minus 8. Problem A says calculate the molar solubility of solid lead to fluoride in a 0.5 molar sodium fluoride solution. And B, what is the molar solubility of lead to in a saturated solution? Saturated solution of lead to fluoride. See, based on what we are going to observe, what effect does the presence of a common ion such as the fluoride ion have on molar solubility of the compound lead to fluoride? Okay, so those are the three questions that we want to look at. So first of all, in order for us to answer this question, we need to take certain considerations. So in question A, we are asked to say, calculate the molar solubility of solid lead to fluoride in a 0.5 molar sodium fluoride solution. So we already have a sodium fluoride solution that is ionized according to the equation given here. Now we are saying we add lead to fluoride. So what we are doing is to increase the concentration of fluoride ions, 2F to the minus, like that, aqueous. So what we are saying is that we already have the concentration of fluorine, so we are adding more fluoride ions. What is the effect? So let's write here the equation. So this is already there. What we are trying to do is to add more fluoride ions. So we are going to have an ICE table for fluoride, or rather for lead to fluoride. So the solid form of it doesn't do anything, so it remains the same. But in ionic form, at initial, you have 0, you have 0 here. The change is plus x, the change here plus 2x. The equilibrium concentrations, you have x, and you are going to have 2x. Now, the KSP expression will be equal to the concentration of lead 2 ions times the concentration of the fluoride ions raised to the power 2. If we substitute this, we are going to have x times 2x squared. Okay, 2x squared. Now, remember that we initially actually have some amount of fluorine already, which I think I would have forgotten here. So we already had in solution a 0.5 molar. So our initial actually for the fluoride is not 0, but it's 0.5. So that at equilibrium, what we are going to have is, pardon me for this, 0.5 plus 2x. So that our equilibrium concentration, therefore, here becomes x times 0.5 plus 2x raised to the power 2, or 2 squared. Okay, 2 squared, like that. Okay, now remember that we've said that the solubility of insoluble substances is very, very minimal. Therefore, we can assume here, okay, we can assume here that even if we were to add 2 of x, or 2x to 0.5, the value will not change so much. So we are saying here that, let me try and put it in a different color. So we are saying here that since the solubility of these insoluble substances is very, very small, the value of 2x will still be very, very small, such that it's as good as just leaving 0.5. So we can say 0.5 plus 2x is as good as, or rather it's approximately, let me put approximately, it's approximately equal to 0.5. So if we do that, then we are saying here in the expression that the KSP expression is as good as saying x times 0.5 squared. So that if we do that, then we are going to say the KSP value, which we have been given to be 4.0 times 10 to the minus 8, that becomes 4.0 times 10 to the minus 8 is equal to 0.25 x. Okay, so we divide both sides. by 0.25, and then what we are going to have is actually, so we said 0.25 this side, divide by 0.25. So our x value becomes 1.6 times 10 to the minus 7 molar. Okay, so the molar solubility, therefore, so molar solubility of lead to fluoride will be equal to 1.6 times 10 to the minus 7 molar. So that is the answer for A. For B, we have been told to calculate the molar solubility of lead to fluoride in a saturated solution of itself. So here, what we are going to do is just to write the reaction equation. So lead to fluoride, solid, giving us lead 2 ions in aqueous plus 2 fluoride ions, like that. Again, we write the ICE table. Let me put a different color. So the ICE table, here, no change. The change, at initial, we have 0 and 0 here. Since it's the solution in itself, the change is plus x, and this side plus 2x. Okay, then we can now write the KSP expression. That will be equal to x times 2x raised to the power 2, which gives us 4x cubed. Therefore, we can say 4.0 times 10 to the minus 8 is equal to 4x cubed. We divide both sides by 4, and then we're going to have x to the power 3 is equal to 1.0 times 10 to the minus 8. So raise this to the cube root and raise this to the cube root. The value of x is equal to 2.15 times 10 to the minus 3. So what this means is that the molar solubility of lead in the absence of a common ion is equal to 2.15 times 10 to the minus 3 molar. So that is the molar solubility. The last part, C, asks us what effect the presence of a common ion is. So if we compare 2.15 and 1.6 times 10 to the minus 7, you'll see that the presence of a common ion actually reduces the solubility. So we can say here that the presence of a common ion decreases or reduces the solubility of lead 2 ions. So that is what it means. That is what is observed, and that is what obtains whenever you have a common ion. So you expect that a common ion will have a significant effect on the solubility of the common ion of interest. Okay, so this is the end of the lecture on solubility products. Thank you so much. Stay blessed.